before we get into it? Anybody have open questions? Any concerns, comments? Any big homework questions? Small? What's up? Any questions? So if you have, can I zoom in on this? So if I have 5 plus 9 minus 3, those should be executed in sequence. If you do 7 minus times divided by plus times 6, it's only that last operator that you hit that's going to count. Is that what you're asking? So does it solve it left to right, or does it solve normally? Left to right. So we don't worry about order of operations at all. We can talk about this more after class. We'll chat about it. All right, any other questions before we get going? Yeah. What is it? How big is the automated testing? I mean, pretty big, but not ridiculous. I mean, I'm testing all the functionality in the document. So you have to have everything working. Even if one open. Yeah. Yes. What do you, yes, you have to have everything in the spec coded. I mean, if you're building a calculator or a microwave and there's something that's broken on it, you're not going to go sell that. It's got to work. All right. I don't think anybody really wants the homework help anyway. You're all talking to each other, so let's get into some new content. You're all eager to learn more things, and I like it. So let's talk about recursion. So we talked about it a little bit on Wednesday in the context of sorting. Today is all recursion. I got 2 examples. We'll go in fairly in depth. If we have time at the end, we'll go into the code, maybe step through a debugger, and take a look at how these work. So the lecture question today is actually one you've seen before. Compute the factors of a number. There's only one small change I made to the original question, is the input 1 should return an empty list instead of the list containing just the value 1. So other than that, you've seen this question before. But of course now we can't use var, and the intended solution is recursive. How do we throw recursion at this to solve the same thing? How do we solve this problem recursively? There's no testing checked by Autolab, but you already have your tests. Just update the input 1 to return an empty list instead of a list containing 1. And you have those tests that you can run to test your own code. I don't have to test your tests because I know you already have them. I already checked your tests. There's no point in doing it again. All right, so let's look at some recursion. We saw this example way earlier in the class. I just rewrote the code a little bit to get rid of the var. Just in the spirit of the current assignments. Oh my goodness. Speaking of current assignments, my goodness, I almost forgot. So we do have the next two assignments are up. So for those y'all really are eager. All right. So the notorious genetic algorithm, many of you have heard of this. My TAs like to spread the word a lot. Genetic algorithm. So a quick overview of these two assignments. I won't go through the whole docs, and they're still being updated a little bit. I want to work on my wording of recommendations. I feel like I didn't word the document as well as I could have, and we'll get the videos and the GUIs and everything up, and the graders, of course. So genetic algorithm is a way of solving problems without actually solving problems. It's somewhat of a machine learning technique, though it's more of a guess and check technique. I don't know the quick one-liner to be able to describe a genetic algorithm. It's something you got to get in there, get your hands dirty, and get used to. The genetic algorithm, it's a very sophisticated, randomized guess and check algorithm that will write in a generic way that can solve any problem where you can measure the results of a given input and be able to create those inputs in a generic way, if that makes sense. That'll make more sense when you get in there. But we'll give some cost function to the genetic algorithm and some way of generating potential solutions. And the genetic algorithm will generate a lot of potential solutions, check their cost, find the min cost solution, and then work with that, mutate that, and work with those best solutions to be able to get closer and closer to an optimal solution. So that's what genetic algorithm is. There is an expansion objective to genetic algorithm. This one is pretty intense. I'll say right off the bat, not all expansion objectives are created equal. This one is to use a genetic algorithm to train a neural network to be able to identify irises using a data set. It is pretty intense. If you're into machine learning, you want to learn about AI, definitely go for it. It took a while just to get that created and get the documentation and everything set up for that structure. So if you're interested in that, please go for that. It's as much as I could do to get a cool machine learning application that's actually palatable for a 116 student. If you're up to speed on all the content, all the material, that should be palatable for you, at least. Difficult still, yes, but palatable. And then recommendations, giving the buying patterns of a data set of customers. We have about 400, I think it ended up being 475 customers in the final data set, and 35 items showing the quantities of which items each customer has purchased. A new customer with no purchase history is viewing an item. What other items do you recommend to that person based on how that item correlates to the buying patterns of the other customers in the data that we have? That's our goal for recommendations. It's going to be a lot of statistics, computing standard deviation, computing correlation, and then finding the max K correlated pieces of items with an input item. So a lot of statistics for that one to be able to get the recommendation system. And of course, with both of these, no mutability. We want to force the functional programming way of thinking using functional programming methods, which we'll dive into headfirst on Monday, using recursion when applicable, and getting the job done without var in general. So those are the new assignments. Feel free to take a look, especially by tonight. You'll all be done with the OOP applications. Get your hands on some functional programming and have fun with them. All right, so we'll need some more functional programming to be able to do those assignments without var. So let's take a look at another recursive example. So we've seen this one before, but let's talk more about the recursive side. Last time I showed this to show stack frames, and we'll see stack frames again today. But today I want to focus more so on, on the recursion details, because at this point I'm expecting you to write recursive methods, so we better talk about how that works. So this geometric sum is going to sum the values from the input down to 1, So geometric sum of 3 is 3 plus 2 plus 1 equals 6. And we want this recursive algorithm to be able to compute that. To design this, we can go through the steps that we saw in the previous case, the previous slide. So I want to refresh that approach. I'm going a little out of different order than I did in the other slides. But we have some base case where there's some trivial input-output behavior. What's a very trivial case where I know that this is going to be true? Well, if n is less than or equal to 0, I'm going to return 0. That's just the way I'm defining geometric sum for this instance. Actually, don't recall what the mathematical definition is for the geometric sum of a negative number. I'm just going to say it's 0. My base case could have also been 1. Just an input of 1 is going to return 1. The sum of all the numbers from 1 to 1 is just 1. But some base case where there's a very trivial input-output behavior where I know the answer is right. That's going to give our recursion something to grasp onto, something to start with, and then we'll start building up bigger solutions starting with that base case. This, I haven't made the connection yet, but if you should be in 191 at this time as well. If you're talking about recursion, I should look at their schedule, see, have you talked about recursion yet in 191? No. Oh, well, that connection is going to be lost. Well, when you start thinking about recursion in 191, or when you start thinking, induction. When you start talking about induction in 191, think about recursion in 116. They're very connected topics. But this is like your base case of your induction proof when you get to that part. And then we have the recursive step, the other side of this. If we don't hit a base case, we're going to hit the recursive step. This is some logic that's going to make a recursive call. It's going to put another method call on the stack when we hit the recursive case, and then do some logic based on the assumption that a recursive call is going to return the correct value. So here, if we're going to make that recursive call at n minus 1, we're going to assume that that's correct. And if that is correct, if I am getting the geometric sum of n minus 1, what do I have to do to compute the geometric sum of n? Well, I just have to add n to it. I don't have much more work to do. I just add n to the geometric sum of n minus 1, and that is the geometric sum of n. So I'm basing my logic off of the assumption that my recursive call will be correct. I'm just assuming that it's going to be correct. And if all my logic is sound, that assumption will just end up being correct through the magic of recursion. Recursion's power is going to take over and just actually be correct. And finally, making sure that our recursive calls get closer to the base case. This is so critically important. Our recursive calls have to get closer to the base case. If we don't get closer to the base case, we're going to hit infinite recursion. We're going to overflow the stack. We're going to blow things up pretty quick. So here, I'm getting an input of n. I'm only making recursive calls of n minus 1. And my base case is n less than or equal to 0. So if I'm always decrementing n, I'm always getting closer to that base case condition being true. And there are some things we have to worry about. The reason I have less than or equal to here, what if someone smart puts -5 as the input here? I want to make sure that's not going to blow up my program. So even if somebody does put crazy inputs in like that, I'm just going to return 0 for that case. So I'm always getting closer to my base case if I'm not there already, because my recursive calls are always calling on a smaller value of n, and my base case is handling 0 and anything negative. So if I have a negative n or 0, I'm already in my base case. If I have a positive n, I'm always getting one step closer on each recursive call. This is so important, or else that assumption that this is going to return the right value isn't going to be true. If I have n plus 1 there, I'm never going to reach my base case. I'm never going to start returning values, and all my logic is going to blow apart. The recursion doesn't work if this is not the case, if our recursive calls don't always get closer to the base case. All right, so let's jump into the middle of an execution of this program. Earlier in the semester, we stepped through this one step at a time. We went through it really slow. just to talk about frames on the stack, I'm assuming you're pretty good on frames on the stack. So let's jump to the middle and just look at how the recursion works, because this is where it can get tricky to visualize what's going on with the recursive call, especially when I'm just saying, oh, just assume it works and then it'll work. What does that really mean? What do I mean when I say that? So let's jump right through the execution of this. And this time when I put frames on the stack, I'm going to remember what line they're waiting for when they're called. So we started with main. We called compute geometric sum on line 11. So main, when we get back to that frame on the stack, we're going to resume execution at line 11. We talked about this last time, but I didn't make it explicit in the slide. So I want to make sure that's explicit so it can help us think about this recursion. So main is waiting right here. That called compute geometric sum with 3. Base case was false, so we entered our recursion. Called geometric sum of n minus 1 of 2. Put a new frame on the stack, and that frame is sitting at line 5, waiting for that return value of that next frame on the stack to return. Once it does return, it's going to resume execution on line 5 and continue with the end of its method. That method, base case was false, got stuck on line 5, making the recursive call. Made that recursive call with n equals 1, with an input of 1. And here we're on this call. The base case is still false. We hit the recursive case again. And we're about to make another recursive call with n minus 1. N is 1 at this case, so we're about to make a recursive call where the input is 0. So we're at the point where we're about to hit the base case. That's where we are in the execution of this, at this snapshot in this execution. So we have all these frames on the stack. We have our top level frame that we're really concerned with. What is the geometric sum of 3? And to get that done, to get that computed, we put these other frames on the stack. Next thing, we're going to get that frame of 0. We're going to be pointing at line 1 and executing this. We took our parameter, assigned it the argument, and we have this variable n on the stack with a value 0. Our base case is finally true at this point. So we finally hit the base case. We stopped the recursion. We're going to start returning values now, which means we're not in big trouble. We didn't hit that infinite recursion. We're actually going to get some return values here. Once we hit this 0, this is the last line of execution. This is the last expression that's evaluated in this method call. So we hit the end of the method. This frame's going to return whatever the last expression was, which was 0. So we're going to return 0 to the next stack frame, give it that value, and that frame is going to pick up wherever it's pointing, wherever its program pointer, we call it, is pointing at, which is line 5, waiting for compute geometric sum of 0 to return. So we get that return value of 0. Compute geometric sum resolves to 0. We take n for this stack frame, which is 1, plus that 0. We're at the end of our method, so that's going to be our return. That's going to be our return value for this frame. We're going to return 1, destroy that frame, give that back to the next frame on the stack. It gets that return value of 1. Its value of n is 2. It's going to compute 2 plus 1. Resume its execution. That's its last line. It's going to return. It's going to return back to this frame. This frame is going to resume on line 5. Compute 3 plus the 3 that's being returned. Compute that. Return that. We're going to end up returning 6 from that top level call. So this is how our recursion, even though we just assumed this was going to be true, it actually ends up being true as long as we hit our base case. So our base case, we know that's true, we can verify. that's true. It's supposed to be a trivially simple case with a simple input-output behavior. We know that's true. So that second to last call, so our base case, we know that's true. We're going to return the right value. Then our second to last call is where the recursion really starts working for us. We were just assuming that compute geometric sum, this recursive call, was true. But in the second to last call, the one right before our base case, that's of course going to be true because it's our base case. So this is of course true right here because it was our base case. Input was 0, we just returned 0. Nothing to really think about there. So we're assuming it's true, but it is true in this case. And then the rest of our logic flows. Okay, that was true because it was our base case. Now let's work with that. What do I have to do to compute the geometric sum of 1? I'm going to add n to that 0 and return that. So now when we get back to this frame, where things start getting a little larger, a little more work being done. I mean, not too much for this example. We get that return value from the second to last step of the recursion, that second to last recursive call that got the base case, which was trivially true, did a little logic under the assumption that that was true, returned a value, but now my assumption here is true too. Well, compute geometric sum, this call took the base case and added 1 to it. Well, that's true because our logic in the recursive case is sound. N plus the geometric sum of n minus 1 is going to be the geometric sum of 1. That logic is sound. So when I get this return value, it was the geometric sum of 1. I'm going to add 2 to it and return that. We get back to this top level frame. By the time we get back there, all the logic flows all the way from the base case all the way up to whatever we were initially computing. As long as our logic in our recursive case flows, our base case is true, and our recursive calls are always getting closer to our base case, we're going to end up with that right answer. We're going to have this correct value in that top level call because our assumption ends up being true because it's one, trivially true, and then just true by the logic that we execute in our recursive step when we're getting the return values of the base case. Recursion. Then finally we get back to the main frame. It picks up its pointer at line 11 and finishes doing its stack stuff that we've seen before. Are there any questions on this? Is recursion starting to sink in a little? I hope. Okay. And admittedly, with an example like this, compute geometric sum. I mean, it's why I use a simple example to start with recursion, but we can get what geometric sum is. So what about when the example is a little more complex? We're about to jump into anagrams, so if there are any questions on geometric sum, please ask them. Because if there's anything you're missing on geometric sum, you're going to be sunk when we talk about anagrams. Yes, thank you.
So with your if n is less than or equal to 0, return 0. So if you don't have something that just returns a straight integer, it doesn't include recursion, then that's when you get that stack overflow because it just keeps repeating.
Yes. Yeah, you had to have some condition in your method that's not going to make a recursive call. That's the critical thing here. So if every time we call geometric sum, we end up calling geometric sum, we're just going to have this chain reaction that's out of control. At some point, there has to be some condition where we're not making another recursive call. That's one of our primary goals in recursion. One, we have to shut off the recursion at some point, and that's our base case. So we'll have some conditional, and when this is true, we're just going to return without making a recursive call. If there's a recursive call in our base case, it's not a base case anymore, and we're going to blow up our stack. We're going to be in big trouble. And stack overflow, absolutely. So if we have a base case that doesn't make a recursive call that we're eventually hitting on every path of the recursion, we'll see just one recursive call today. But like for merge sort, we had 2 different recursive calls. Both those recursive calls have to eventually get down to the base case. And all the recursive calls that they make, everything has to lead to a base case, or else you got that infinite recursion. So you have to get to a base case on every recursive call. Critically important. Okay. Is there no more questions? Let's talk about anagrams. This code is going to look a little scary at first. We haven't talked about most of these things. So don't get too frightened right away. I just want to start teasing the functional programming style of working with data before Monday. Monday, we're going to dive headfirst and talk about all kinds of different things we can do with this idea of first-order functions, which you're seeing all around this code. We see quite a few things here that you haven't seen before. So don't get too shocked. I'll talk about each of these briefly at the end. I have some slides on them. But for now, I want to focus on the recursion, and we'll assume that my logic does do what it's supposed to do in the recursive step, and I'll reiterate what it's supposed to do from last time that we saw this example. So first, our base case. And just a reminder, we want to find all the anagrams of a string. So given a string, what are all of the ways that we can rearrange the characters to generate another new unique string? So we want to compute every anagram of an input string. If the input is length 1, it is itself its only anagram. Trivial case, the input of size 1, we really don't have to think about this one. If I have a string of length 1, it is its only anagram. I'm going to return a new list containing just that string, and I have successfully computed all of the anagrams of a string of length 1. And this is how our base cases are going to feel throughout recursion. Should be very simple cases, very easy cases to compute. Input length 1, just return it. We could also do input length 0 if we wanted to add another base case here, or just have input length 0 would still work. Input length 0, return an empty list. Done. Base case should be simple. And even though, so one thing, so implicitly in here, I do actually have a second base case of 0, just because this loop will not execute, and my recursive calls are happening only in that loop. So I technically have a second base case here of 0, because there's no recursive calls that are made there. So I don't have an error. If you do input empty string, it does return an empty list. Right? Oh, actually, I don't know. Did I test that? Yeah, it should. I believe it does. So I do have an implicit one. But also note, and this is common with recursion, is that even when we're returning an entire data structure in this case, or the sum of the geometric sum in the other case, even when we're returning something that contains a lot of information, the sum of all the numbers 3 to 1, or n to 1 rather, all the anagrams of a string, even though that's what we're eventually returning, we're usually only initializing that in the base case, and then in the recursive step we're adding to that. So in the base case, this is the only time where we actually create a new list that we're going to start adding to as we start building more and more anagrams. In the other example, the base case was the only time where we actually initialized an integer, and then beyond that, we're adding to that one integer that we kept, that we initialized in the base case. In the recursive step, you're going to have to, if you if you haven't studied functional programming yet, there's no expectation that you have. You have to take my word for it that this is doing what it's supposed to do. It's doing the same thing that we did last time we talked about this. I just removed all the vars, which forced me to use a functional programming style approach at this. So with this, we're taking the input word, checking each letter one at a time. For each letter, we're removing that letter from the string. So you can see that code was preserved, that creating the new string, removing that letter from the string as we're iterating over all the characters, and then we're making our recursive call on that new string. So we're assuming, and then when we get that recursive call back, we're going to append that character that we removed to the end of each anagram that was returned. So we're assuming that this recursive call that we're making is going to return all the anagrams of that string. So we're just assuming I give Anagrams, the method that I'm currently writing, a string, that it is going to return all the anagrams of that string. I'm just going to assume that that's true and work all my logic based around that assumption. So if this does return all the anagrams of that string, then I'm going to append the character that I'm currently considering to the end of each one of those strings, and then add those to my final solution set. So if Anagrams does what I want it to do, then any input that I have here, this must be the correct logic, as long as you believe me on all the functional programming stuff that I'm using here. So as long as Anagrams is right, then Anagrams will be right. It's all circular logic, seemingly anyway, when it comes to recursion. And the recursive step is circular logic. If the recursive step is right, then the recursive step is right, then the recursive step is right, then the recursive step is right, which is why we have to have that base case to give us something to grab a hold to. That's the one part where we're saying, here's where the actual logic happens. Here's where something actually happens. If we have an input of length 1, here are all the anagrams. That's where this assumption actually starts to be true, is with the base case. And then as the base cases start returning, those assumptions we made are true. And as long as our logic is true, based on that assumption, as long as we're doing the right stuff, based on that assumption being true, our whole algorithm is going to end up being true. Because the base cases will return, those are true. Our logic is going to combine those base cases and return. That return value is going to be correct. The next step of the recursion is going to combine all those return values and return that. As long as our logic there is correct, that return value is correct. And it's going to go all the way up to the top level recursive call. And that recursive call will end up being correct based on the base case being correct, our logic being sound, and of course, getting closer to our base case with each recursive call. So our base case is an input of length 1. If I get an input of length greater than 1, again, we can test, we can go to the code and check, but I should be handling the inputs of length 0. Strings can't have negative length, so I have some length greater than 1 if I'm hitting my recursive step. I'm removing one character, getting a string of length n minus 1, of the input length minus 1, and then making my recursive call on that smaller string. So I've successfully guaranteed that I'm going to get closer to my base case with each recursive call because I just subtracted 1 from the length by removing a character from that string. So my base case looks right, my logic seems sound, and my recursive calls are getting closer to my base case. Sounds like I have the formula for a winning recursive method. Which I do, of course it works, of course I tested that. I don't, just that edge case, I might have not tested. I'll have to double check. So we're always going to reach a base case, our logic is sound, our base case is sound. What can go wrong? The magic of recursion, I shouldn't say magic, but the power of recursion takes over after that. and just makes the whole algorithm correct, makes our method correct. And it always seems, maybe it's just me, but it always seems with recursive methods that we shortcutted something. Like there's something that we should have computed that we just didn't end up computing. But this is it. This takes care of it. That recursion kicks in and starts doing a lot of the work for us if we set everything up right. And that base case, when we hit the base case, our assumption is always going to be true if our logic is sound for the base case, of course. It should be true because it's supposed to be a trivial input-output behavior. So once we get to the base case, our recursive step starts kicking in and doing some work for us. If our input is AT, we're going to make two recursive calls, one where we remove T and make a recursive call on A, one where we remove A and make a recursive call on T. Each of those are the base case. We're just going to return them. And we're going to append T to A, the character that we removed. We're going to add that to every element of the returned list. The returned list just has one element, and we're going to add that character we removed to it. Same on the other recursive call. We're going to append A to that returned list that just contains the single string with just the character T. We're going to append A to it, and then combine those two lists to get the overall, all of the anagrams of at. And then it just builds from there. So from our base case was true. Combining two returns of the base case, we can see how that logic is kicking in and doing what we expect it to do. That's going to be returned potentially to some recursive call with an input of length 3 that makes 3 recursive calls. It's going to get all those return values, including at and ta. It's going to get all those return values, append the missing character to all of the lists, all the strings in each list, combine all those, return those to the next level of the recursion. It's just going to keep going until we have one list with all of the anagrams that we need. I feel like there should be more questions. Recursion can get tough. I'm trying to just go slow enough so you have time to digest. Yeah.
So you always want to get closer to your base case with your, like, whatever's in your else statement, usually?
Yes.
Or your recursion?
Yep. Whenever you make a recursive call, this recursive call right here, for example, we have to be getting closer to our base case. If we're not, we risk that infinite recursion. Yeah.
Closer as in, like, you try to, like, are you just trying to make, like, the first if statement, like, false?
I want that first conditional to be true at some point, and I want to hit that base case. So I kind of shortcut my logic by saying getting closer to the base case. To be more specific, on any recursive call, if I keep making the recursive calls and follow the chain of all the recursive calls that are going to happen, I have to eventually reach that base case. If I don't eventually reach a base case, then I have an infinite recursion. So at some point, to stop the infinite calls of recursion, we have to reach a base case, some input of this method that's not going to make another recursive call, or else we're just going to keep putting recursive calls on the stack. We're going to overflow the stack. Program's going to crash. We don't like that. Users don't like that either. So we want to always get closer to the base case, meaning that eventually that chain of recursive calls is going to reach a base case and finally start returning and destroying stack frames instead of putting more frames on the stack. That's what we're after. We want to eventually end this execution and actually get our return value so our program can keep processing whatever else it needs to do. Does that make sense? Okay. All right. Let's talk about some of these functional programming things. Any more recursive questions before I talk about this new syntax and this new stuff we're seeing? All right, so let's talk about a few of these functional programming things. Let's give a quick overview, but we'll, again, like I've been promising, we'll dive into these things on Monday. And Monday we'll do a lot to prepare you for those homeworks to be able to write those things without var. So let's just go through these. So yield, it's a very nice little keyword. You put it right in between where you start your loop, where you define your variable you're iterating over, and before the body of the loop. If you put that little keyword yield right there, instead of just executing the body of the loop for each element that you're iterating over, this is going to create a data structure containing all of the elements formed by taking the last expression that's evaluated in each execution of the loop. So I'm looking, when I have this yield here, I'm looking at the last expression that's executed. This one is going to make my recursive call, get all the anagrams of new string, and then append the character that I removed to all of those values in that list, in those anagrams that were returned. So I'm going to append that character to each of the values of the return of that recursion. I'm doing that for each character, so I'm going to end up, this is a list of strings that I'm creating. I'm doing that for each character, so I'm going to end up with a list of strings. And when we use yield, it's usually, it's going to give us a data structure of the type that we're iterating over, which is a range. It's at least going to try. So it's going to try to put this into a range and not be able to because they're lists of strings. It's going to put it in some other data structure type. So we usually throw this whole thing in parentheses and give it a to list if we want to use it as a list. So I have my lists of strings that was generated from this loop using yield and converting the result to a list. So that gave me a list of strings. So instead of having some accumulator variable that I append to and reassign every single iteration of the loop, I use this keyword yield. This generates one data structure, and then I assign it to my value here. There are some advantages of doing this. This isn't just to restrict you and force you to use new things. That is a big part of it, I'll be honest. But when you use things like this, the Scala compiler is able to do a lot for us when we do this. The Scala compiler and the yield functionality itself, all the features built into the language, are able to work for us and optimize our code in ways that we're just not, might not think of doing, might not bother to do, or we just might not have several decades to look at our code to be able to optimize as much as they have with these built-in algorithms and the built-in compiler, or not built-in compiler, but with the compiler. So yield is going to just not care what happens in the intermediate, but it's going to return that data structure that we want. Map is going to do something very similar to Monday's lecture question, this Monday's, not next Monday's, where you took a list and a function and created a new list based on that function. Map takes a function and does exactly that. It applies this function to each element of the input data structure and creates a brand new data structure with those elements, but with that function applied. The new thing here, besides map, of course map is new as well, but I'm using a little bit of shorthand here to define my function. I could do parentheses, s of type string, and then the equals, the arrow with the equals greater than, and then input dot char at of I and append it to s. I could write my function in that same syntax that we used before. If I want to show off some new syntax today, you can shorthand this a little bit with the underscore. I can say underscore plus that character, and the underscore is going to be the input of the function. If there's only one input to the function, and if the type of that input can be inferred. So since I'm calling map, I'm calling it on a data structure. This data structure happens to be a list of strings. So when I call map, Scala is expecting a function that takes one string. So in this situation, I can use this shorthand. I can say underscore. That's going to be my string input. I don't have to give it a name or anything. It doesn't need a name. We're just going to call it underscore, and I give it the body of the function only. to be able to get that functionality I want, to be able to append this character to all the strings of this list and return that as a new list. I get to do that with some pretty compact code, and you'll see that with all this functional programming. It's very expressive. You can do a lot without a lot of characters, without a lot of code. You can get a significant amount done. It's very descriptive, I should say, expressive, descriptive. You basically tell your program what you want to do, not how to do it. Hey, code, I want to take this list and create a new list with this function applied to it, instead of creating a loop and an accumulator, a new list, and appending to it, which is more of, hey, program, here's how you get the job done. I'm saying, hey, program, just do this. Then a few more. The Scala data structures have a lot of methods that just make our lives easier. Flatten. In this, I'm taking a list of lists and calling flatten. It's going to convert my list of lists to a single list containing all the elements in all of the lists. One word, just one call, I can get that done. And then distinct is going to do what we had trouble with last time, not trouble with, but what we had to address last time we saw anagrams, is remove all the duplicates from the list. So we don't have duplicate anagrams floating around. So every time we have a double letter in our words, we don't have double the anagrams.